So here's another example that we can look at using chain rule, and we'll try and set it up exactly how the pattern that I want you to try and use in class. And so what we've got is x of t equals cosine of t squared plus 1, and we're talking about an object that moves along the x-axis. So, and this is position. Remember, position, derivative is acceleration, or is velocity, and the derivative again is acceleration. So if we want to find the velocity, we need the first derivative of this. And so we need to find dx dt. And the way that we're going to do that is we're going to find dx du, and we're going to multiply it with du dt. And again, what we're wanting to happen is we're wanting these du's to cancel out. And notice when they cancel out, I have exactly what I need. So let's let u equal the inside part. We're going to let u equal this inside part right here. So we're going to say, hey, u equals t squared plus 1. So du dt is equal to 2t. We're going to say that x of u is equal to the cosine now, not of t squared plus 1, but of u, because look, we've picked what u is going to be. And so dx du is going to be what? Well, what's the derivative of the cosine? Negative sine u. And now we put those two things together, and we're going to end up with dx dt and that's going to equal 2t times negative sine of u, which is, whoops, not 2. Let's see, let's get rid of that guy, which is t squared plus 1. So how would we look at this as our final answer? We would simply say, for our final answer, that negative 2t sine of t squared plus 1 would be the velocity of the particle. Okay. Well, what about taking the derivative, differentiate, find derivative of x squared plus x. Wow, what's going on here? Well, x squared plus x is inside sine. So again, we're going to do it this way. We're going to find dx dy is going to be equal to dx du times, whoops, not dy, du dy. Okay, so we need to figure out what u is. U is going to be the insidemost part. Here's u right here. U is going to be this inside guy. So u equals x squared plus x. Du dx is equal to 2x plus 1. Okay, that gives us then for y going to be equal to sine of not x squared plus x anymore, but u. We're replacing x squared plus x with u. Okay, that's why we picked it. So now we're going to go with dy du, and the derivative of the sine is the cosine. Okay, and so when I multiply the things together, dy dx, I wrote that completely upside down. And let's trade these two guys. So dy dx is equal to dy du times du dx. So dy du is cosine u. What is u? U in this case is x squared plus x times du dx. What is du dx? Well, du dx is let me see, having a hard time getting my stuff straight here. Du dx is going to be 2 times x plus 1. Okay, so what is this going to look like when you're all done? Well, it could look like where you're at right now. There's really no need to FOIL all of that out unless you wanted to move the 2x plus 1 into the front. It's just going to be kind of a little bit of a longer problem. But this is a good answer for using your chain rule. Okay, so look for that inside thing. That's your u. The outside thing is the function for y. And we're going to take derivatives of both of those. Again, it's going to take a little practice, and think about that peanutty M&M. Start with the peanut, go to the chocolate, go to the candy shell. Okay, this is going to be a long one. There's 3 things that are going on here. We've got on the very inside, very center, smallest part is 2t. Next in level, we've got this guy right here, 5 minus sine 2t. And then lastly, on the outer edge, we got the tangent of all of that. So let's just organize this out and look at exactly what has to happen here. Okay, so if I take g prime of t, that's the same thing as taking the derivative with respect to t of the whole thing. All right? Okay, but we've got a lot going on here. So what we're going to do is we're going to look at the derivative of this guy first. Okay, the derivative of this guy first. So the derivative of the tangent is secant squared. So we're going to have secant squared time, and we're still going to have 5 minus 2 sine 2t here. And then we go to the next one, and we're going to be times derivative of the next part in, and that's going to be this guy right here. Let's see, let's get green ink. 5 minus sine 2t. Okay, and the derivative of that guy is going to be, again, when we just look right there at the sign, the derivative of the sign there is cosine. So now we're going to have secant squared 5 minus sine 2t times derivative of 5 is 0, so minus cosine of 2t, and then the final derivative times the derivative of 2t. And the derivative of 2t is just 2. So our final full-length answer is going to be secant squared 5 minus sine 2t times negative cosine 2t times 2. It's really a long answer, but this is a good answer. The only way you might clean it up is by putting that 2 and the negative sign in the very front, so you have it like this. There's a big chain rule problem for you. And you may need to watch this a couple times to try and catch everything that's going on there, but if you'll just do one piece at a time and take the derivative and move in, everything will be nice and smooth. So in this example, what we're going to do is look at a parametric equation where you've got like a t equals something, and or you have y equals t equals something and x equals t equals something, And so how do you take a derivative of that? Well, there's a way to take a derivative of a parametric equation, and you have to take a derivative with respect to y and take one with respect to t, and when you divide those two guys, the dt part cancels out. It's all math. So if you'll just notice right here, if I have y equals, or x equals, or y equals, so if I have, let's just go with x equals something t and y equals something t, then when I take derivative of that, I'm going to have dx dt. And when I take derivative of this one down here, I'm going to have dy dt. And so when I put the derivative of y, dy dt over dx dt, I end up with dy dx. And keep this in mind, if you'll notice, when you're working this out, I need dy dx in the numerator. Well, this is just like slope. So on the top, this is my change in y, and on the bottom, this is my change in x. So I've got to have that slope part to do the parametric equation correctly when I take the derivative. So how does it work? Well, it works like this. Find the line tangent to the right-hand hyperbola branch defined parametrically by x equals secant t, y equals tangent t, from negative pi over 2 to pi over 2. So how does all that work, you might ask? Well, here's how that works. What you're going to do is find dx dt. So we're going to find dx dt. And when we find dx dt, we're going to get, let's see, secant t tan t. And we're going to find dy dt. And when we find dy dt, that's the derivative of the tangent part then, so that's going to be secant squared t. And then we just do our division, secant squared divided by secant t tan t. So what we're going to end up with is the y part on the top, so secant squared t, and then the x part on the bottom. And so we'll put x in this mustardy color. So this is going to be secant t tan t. Okay, and what this really is, this is dy dx. That's what dy dx equals. Well, we can reduce this just a slight little bit, and we end up with secant t over tan t. Okay. And then if you think about this, if I've got secant t over tan t, tangent, this is like saying secant t cotangent t. And the cotangent, if we think about what these guys are now, because we can clean this up even more, 1 over secant, or secant is 1 over cosine t. Cotangent is cosine t over sine t. And so the cosines cancel out, and I'm actually going to be left with 1 over sine t, which is cosecant t. That's my derivative, okay? So, find the line tangent to the right-hand hyperbola branch defined parametrically by, and then it gives me this thing. Well, that's going to be my tangent line, my tangent slope is going to be cosecant t. So dy dt is equal to the cosecant of t. That allows me to find my slope at any point along this line. Okay. Well, what about if we've got a point? Let's say we've got a point that is square root of 2 over n 1, and let's say we're interested in t equal pi over 4. Okay. So if I know what my slope is, then I can find the slope of my line by putting pi over 4 in for the cosecant of t. And when I do that, this becomes the cosecant of pi over 4 And what does that equal? Well, that's equal to 2 over the square root of 2, which reduces to the square root of 2. And you can use a trig table to get this answer. And so this is the slope then of my tangent line. And if I know a point on the line and the slope of a line, can I write the equation of the line? And the answer is yes. My equation on this guy is going to be y minus the y coordinate equals the slope times x minus the x coordinate. And that's all you need to do on that guy. There's using a parametric equation to find a derivative, and then taking that and finding the slope at a specific point. All right, let's look at now using the power rule with the chain rule, and we're going to use it with a trig function so we can really investigate what's going on here. And basically the power rule says this: if we have some function to a power, then we're going to do the same thing we always do, except now when we're done taking that power and multiplying with whatever's in front, we're going to take the derivative of the inside. So think along the lines of, if for this guy, I've got y equals sine to the 5th power x. We want to find the slope of the tangent line to that curve where x is pi over 3. Think about it this way. I want to take the derivative of u to the 5th power. Okay? And when I do that, dy du is 5u to the 4th power. Okay, but now I need to multiply by du dx. Well, let's let u equal sine x. So du dx is equal to the derivative of the sine of x, which is just cosine x. So how does this work out now? Well, anytime I do chain rule, the chain rule is dy du times du dx. And when I do this, if you'll notice, the u's cancel out. And so when my u's cancel out, I'm just left with dy dx. So dy dx in this case is equal to 5u to the 4th. Remember, u here is sine. So 5 sine to the 4th times cosine x, which is my du dx. Okay? So here's my chain rule with a power, and now this is equal to my slope. This is equal to my slope. Well, what does that mean? That means that all I need now is an x value, and if I have an x value, I can find a matching y value to get a point, and then I can use that same x value to find the actual slope of the line where I'm interested. So if we plug in pi over 3 for x, that's right here. So y equals the sine of the 5th power of the sine of pi over 3. And the sine at pi over 3 is the square root of 3 over 2. So it's the square root of 3 over 2 to the 5th power. So if you work that out, 2 to the 5th power is 32. And then on the top, that's going to be 9 square roots of, 9 square roots of 3, I think. Oh, we just need the slope. Well, we're going to get a slope and a point. So the square root of 3 to the 4th power is 9. So it'd be 9 square roots of 3. So here is x. Here is y. So I've got a point. Okay, the point is pi over 3 and 9 square roots of 3 over 32. There's my point. My slope then, I'm going to take that square root of 3 and put it in right here and right here. Not square root of 3, the pi over 3. And when I do that, what I end up with is 5 times the sine of pi over 3. Now we figured that out. That was the square root of 3 over 2. So 5 times the square root of 3 over 2 to the 4th power okay, times the cosine of pi over 3, and the cosine of pi over 3 is 1/2. And you can use trig charts, or if you remember what's going on, you could do that as well. So then square root of 3 over 2, when you look at square root of 3 to the 4th power, that's 9. 2 to the 4th power is 16. So this is my shape, 5 times 9 over 16 times 1/2. And when you work that out, that's going to be 45 over 32. That's your slope. So now I have a slope, I have a point, and so the equation of my line then is going to be y minus the y coordinate, 9 squared, so 3 over 32. There's no need to write this as a decimal, equals 45 over 32 times x minus pi over 3. And that's all there is to it. So this problem's not too terrible, but you do have to pay attention and see what's going on. And chain rule requires some practice to see and do, but it's practice that you need to put in so that you can get all of this stuff correct and understand how it's going to work.